Welcome everyone. Today we're very happy to have Jacob McNamara from Caltech, who's going to tell us about reflections on Parity. All yours, Jacob.
All right, thank you so much for the invitation. It's really nice to be here. I don't think I've been here since grad school visits. Having a lot of fun. I'm going to be telling you about this project with Matt Reese that is half a phenomenology project, half a project on generalized symmetries, and a little bit about symmetries in quantum gravity. So I'm going to start with some phenomotivation. I think that's maybe at least one phenomenologist here. And so we'll hopefully have something meaningful to say both from a pheno perspective and from a formal perspective. Let me say also, please interrupt at any point with questions. I always love when there's as much discussion as possible. So I'll start with some phenomotivation. So the motivating problem is the strong CP problem, which is the fact that the standard model has CP violation, but the QCD theta angle, QCD, is ridiculously small. It's smaller than something like 10 to the minus 10. So this looks very unusual from the perspective of naturalness. If theta being 0 preserved the symmetry, we would just say that the standard model has the symmetry and be done with it. But because the standard model does not have this symmetry, we need to explain why this parameter is so small. There have been a lot of ways people have tried to address this. I think maybe the most preferred is axions, but I'm not going to talk about axions today. Instead, I'm going to talk about a class of models that are broadly known as Nelson bar models. As far as I can tell, these are maybe a little bit out of style. But what I'm going to be saying is yet another issue with them, so maybe people who don't like them will be happy. So the basic idea is to promote either CP or P symmetry to an exact symmetry. And explain the observed CP violation as a result of spontaneous symmetry breaking in our vacuum. This is difficult to do technically. There's some space of models where you do something like this. The technical challenge is that you need to explain the observed CP violation without running back into the problem you tried to explain and generating a large QCD theta angle. For example, if there are dimension 5 Planck suppressed operators which break CP, then you need the scale of CP violation to be something like 10 to the 8 GeV, which is pretty low. So these models are a little bit finicky. They're difficult to make work exactly. But I want to make sort of model-independent statements. I want to use generalized symmetries and try to make statements that are true in any such model and don't depend on any of the details. So a word of warning, as terminology, I'll use the word parity to mean any orientation, space-time orientation reversing symmetry, which is restored in our model. So this could be parity, this could be CP, this could be a combination of them with a discrete internal symmetry. I'm going to call all of them parity. Some people might prefer if I called them reflection. But in any case, I'm just assuming that my model restores in orientation reversing space-time symmetry in the UV. And I want to understand what sort of universal features just come from restoring some symmetry, which I'm going to call parity. So what is the generic issue? Well, the general issue that comes in any particle physics model where you posit an exact spontaneously broken discrete symmetry is domain wall formation in the early universe. It's a well-known issue.
Do you mean gauge symmetry?
Great, so I said exact symmetry. I'm actually going to say gauge symmetry. So in quantum gravity, we expect that any exact symmetry is gauged. It will be important for what I'm talking about that the symmetry is gauged. Of course, you could talk about models where the symmetry is broken by some effect. Those are not the models I'm talking about. But if the symmetry is broken by some effect, it becomes much harder to explain the strong CP problem. You have to say that the symmetry is broken only a teensy tiny bit by the effect. That also looks weird from the perspective of quantum gravity, as you know, we expect symmetries that are broken to be badly broken.
Another question about the parity. You said it's both spatial both, but you can usually define just have a defined fermions with the conjugate representation. We can just switch it, right? Not necessarily have to involve space inversion.
That's right.
Usually phenomenological terminology. What does that count for your parity? Or
So
you really have to think about the space-time?
I really think about space-time symmetry. So that would fall under the realm of internal Z2 symmetries, and I can, of course, if I have an internal Z2 symmetry and a space-time reversing symmetry, I can combine them in various ways. It's very important for what I'm going to talk about that the symmetry I'm talking about acts non-trivially on the space-time manifold by an orientation reversing action. Yes.
Sorry, I missed that. Why is this important that it's a gauge symmetry?
Why is it a gauge symmetry, not a global symmetry?
Yeah.
I'll talk about that more in a little bit, but the basic expectation in quantum gravity is that any fundamentally exact symmetry is a gauge symmetry.
Sure, but that's the only reason that we care about.
Yeah, you could fully well. So I'm going to be talking about this domain wall issue, and the domain wall issue could only possibly be dealt with if it were gauge. We'll see that even gauge doesn't deal with it, but for global symmetry, it'd be even worse. Yeah. Any other questions? Okay. Yeah, so the generic issue, the general issue with any such model, in fact, any model that has, this issue also comes up when you have an internal Z2 symmetry, is domain wall formation. So the early universe could have cooled through a spontaneous discrete symmetry breaking phase transition, and as it cooled, you can imagine you have some field which has some, potential with multiple minima, and different regions of the universe could settle into the different vacua, leaving behind a network of domain walls. And domain walls are objects of codimension 1, they redshift slower. So if they're stable, then this leads to a cosmological disaster. This might be a little bit too harsh. What I mean is that if they were stable domain walls formed in the early universe, we look up in the sky and we don't see them. So something had to get rid of them. There's basically two options. Assuming I'm not going to break the symmetry. The two options are to inflate them away. So this option is kind of always available to us. We can always just say, well, sweep it under the rug of inflation. But this puts severe bounds on some parameters of our model. In particular, if we want to inflate away the domain walls, we need to have formed them before inflation. And that puts a very severe bound on the scale of inflation. Which there's some parameter space, but it's very constrained.
Do you know roughly what that energy scale is?
Yeah, so this would be Hubble during inflation. Assuming a generic dimension 5 operator violating CP, you can do much better if you invoke some other gauge symmetries to push it to a dimension 6 operator. But if you have a dimension 5 operator, this would have the scale of Hubble during inflation, something like 10 to the 8 GeV, which is much lower than the observational bounds. Possible, but constraining. Yeah.
Sorry, what do you mean a dimension 5 operator is breaking CP? I thought you gauged it.
Sorry, in the EFT arising after spontaneous symmetry.
Oh, okay.
Yeah. This is called the Nussbaum quality problem. You need to not have it feed back into this, and that requires a low scale of inflation, a low scale of CP violation, and thus a low scale of inflation if you try to get rid of them by inflating them away. Yeah. And so the other option, and I think the vastly preferred option from people who have thought about these issues, is to destabilize the domain walls. So this is only an issue if the domain walls are stable, right? If I can form domain walls, but then have them sort of dissolve away into nothingness, then there's no problem with the fact that we don't see them in the current day. And in fact, this option is so preferred because it looks like there's a universal decay channel, or a universal mechanism for decay.
Because you seem to be using Epsilon motivation.
Yes.
Right? Epsilon does not require that to be really space-time symmetry, right? Because you just have to both just, field theory, you get the right amount of
that's right. If you impose, say, some internal discrete gauge symmetry, which
There is a lot of parity for a standard model.
yes. But you would need it to be, you know, very particularly chosen. It would need to be some particular symmetry, Z2 symmetry, for example, under which, you know, the QCD axion, or sorry, not the QCD axion, sorry, the QCD instanton density and whatever other degrees of freedom you have. Yes.
Still, anyway, that doesn't probably have to do with your real credit.
Yes, absolutely. My claim will be about, yes, so I will restrict myself to models in which I've restored a space-time oriented.
Yeah, then nothing, but because you use it so much, so I just...
And in fact, Nelson bar is also maybe not, this is not my area of expertise, but Nelson bar is maybe also too restrictive because there are other models that restore some other symmetry, like, you know, dual, whatever I call it, dual firm, where you have extra fermions that transform, and maybe you don't call those Nelson bar, but those are still within the regime of what I'm talking about.
Just wanted to make sure.
Thank you, good, so what I wanted to say was that I think people mostly don't view this as as the most, earth-shattering obstruction, because it looks like there's a universal mechanism for domain wall decay, which is to first say that our symmetry, or discrete symmetry that we have, is gauged. So this goes to the earlier question of why do I want to talk about gauged parity symmetry. And then I can have domain wall decay via cosmic strings. So if I have some domain wall here, then I can nucleate a loop of cosmic string. So this is an object of codimension 2. You go around it, you pick up your discrete symmetry transformation. And in the symmetry breaking phase, it serves as the boundary of the domain wall. And you can nucleate a loop, which will eat up the domain wall and leave behind sort of conventional cosmology, matter, radiation.
Why is symmetry gauged? It has nothing to do with decay, right? It's a simple thing.
I need the symmetry to be gauged to have dynamical cosmic strings. Right, because...
you're not saying that this is the either option.
No. You need both. You need this and then this. Yeah. So I'm saying that, but maybe I should say that, again, from the perspective of quantum gravity, this is a very natural. Because in quantum gravity, we expect that every symmetry is gauged. So exact implies gauged. And moreover, we expect a complete spectrum of cosmic strings, like the completeness hypothesis. So this mechanism looks, you could say this is not universal in quantum field theory, but maybe it's universal in quantum gravity. So it looks very good. What I'm going to tell you is that while this story works perfectly well for an internal Z2 symmetry, it does not work for parity. And again, by parity, I mean that. So the main result that I'm going to try to argue is that parity domain walls are exactly stable. And parity cosmic strings don't exist. So I'm going to give actually a very simple topological argument as to why this idea of having a codimension 2 cosmic string for parity that would nucleate and eat up parity domain walls is inconsistent. And it's actually a very simple argument.
No, you want to evoke.
Sorry?
No, you want to embed, or that's like...
No, you want to evoke. Well, there's also no you want to embed, right? In the same dimension, there's no way to embed parity in a continuous
Or
sequence.
it can be identified with the words.
In higher dimension, yeah.
So something like this, what do you so next so that it's not the generic, I don't know your actual full argument, but you cannot embed parity in a gauge symmetry if you do something.
Sorry, my argument isn't that argument. My argument is different. I mean, parity in a fixed dimensional theory kind of clearly can't be embedded in U1 because there's no continuous way to go from an orientation reversing, preserving Lorentz transformation, but an orientation reversing one. Like those are just different components. But I should also say, I'll review some of the story and ways of thinking about cosmic strings. You don't need to embed it into a continuous gauge theory to have cosmic strings anyway.
Quick question.
Yeah.
So what's the consequence of this for the standard model? Are you saying we should see domain walls or?
So what I would want to say is that I probably think Nelson-Bar models are maybe not this is a reason why Nelson-Bar models are maybe not what you should think is the resolution of the strong CP problem. So the pheno upshot is that either something else resolves the strong CP problem, like axions or something, or the domain walls are inflated away. You can't they can't decay. And in fact, from a sort of formal perspective, there's a clear way to say this. The reason is that parity domain walls, I'm going to write PDW, are charged under a topological gauge symmetry. So I'm going to argue that parity domain walls carry a sort of topological gauge charge. It's an unusual sort of gauge charge where the gauge flux is given by the orientation of the space-time manifold, or more precisely, a classic cobordism. And this gauge charge has some unusual properties. In particular, it satisfies a weaker Gauss law. But I'm going to try to argue that these parity domain walls carry a topological gauge charge, and because they carry a topological gauge charge, they can never decay. Right? Any object which carries gauge charge, if it decays, it decays to something that also has that gauge charge, and anything with this gauge charge would be a parity domain wall. So they're exactly stable. Good. So are there any more questions about? Yeah, please.
So you may go, how this spontaneous breakdown can be implemented? Suppose you have a field, and it breaks, right? And then you get a bed, and you can just interpret that as a vectorized symmetry evaluation in terms of just a charge, not necessarily involved space. So you...
I'm imagining a pseudo-scalar gets a bed, for example.
Good.
Yeah. or some other mechanism which has an effective pseudo-scalar getting a bed. Yeah.
So I guess these guys always need to be formed in pairs. They come with some...
Yes. So exactly, this is a topological C2 gauge symmetry. And so they can be pairwise annihilated.
Yeah.
But from the perspective of cosmology, you're imagining you have some large cosmology with some domain walls that are like far away from each other. And while topologically they could annihilate, dynamically there's no energetic reason why they would do that. And if you want to annihilate, just destabilize them, get rid of the cosmological process, you really need just one by itself to decay away. And that's what's protected by this gauge charge. This process is what I'm saying is not possible. Yeah.
Can I ask a question?
Yeah.
So you said it's natural from quantum gravity that parity should still be gauged in the UV.
If it's exact or broken.
I see. Should we still imagine that parity is gauged in the UV in the standard model, or?
That's a great question. So, good. So when I say I have a Nelson-Bar model, what I mean is that parity is restored at some scale where you still have the breaking of parity is describable within effective field theory. So in particular, I don't want parity to be restored like above the Planck scale. I'm imagining that parity is restored. In fact, this is the scale where I'm imagining parity. This or lower is where I'm imagining parity is restored. Probably in some very deep sense, parity is restored in any quantum gravity theory in the deep UV. So probably even type 2B string theory restores parity in some sense. But no, I mean that the restoration of parity is happening before the entire gravitational EFT breaks down. And again, that's important for the cosmological question because I'm imagining I have a big semi-classical cosmology. I don't want to just crunch away the universe, for example. Great. Any more questions? Yeah.
A lot of the domain walls, when I think about them, are they infinite? Can they sort of be closed onto themselves, like the surfaces, or are they just Is it very close on themselves? Can they could they have decay just by becoming smaller and smaller?
Yeah, again, this is the sort of pairwise decay. Right, you could have them have some topology like this with some finite domain, and then they can collapse inwards. The problem is that the universe is expanding. And so unless there's some energetic force, there's some force attracting them, which there isn't in this case, right? The two vacua are exactly degenerate, and so there's no force pushing them either way. There's no reason for them to decay. Like you would produce some abundance of them, and they would, some amount of them would decay, but would annihilate, but you would still be left with some. Great, great questions. Any more? Here. Okay. So this is the goal, and I would like to review how to think about about domain walls and cosmic strings and their stability for the case of an internal symmetry, but in terms of some modern language of generalized symmetries and associated operators and sort of topological effects. Because I want to establish some ideas that will let us more clearly think about the unfamiliar case of parity. So, review of an internal Z2 symmetry. So the first thing I want to do is I want to clear up a misconception. Frequently when people think about Z2 symmetries and you ask what is the difference between a global versus gauged Z2 symmetry, of course there's no local propagating vector boson, so it's not so clear what the distinction is. And frequently people say that, well, the symmetry is gauged if and only if there are cosmic strings. And this is wrong. This is not quite correct. And it's very important that this isn't quite correct, because then the entire story I'm telling you would be nonsense, because I'm trying to tell you that you can have gauged parity without cosmic strings for parity. So what does it mean to have a global versus gauged discrete symmetry? A better distinction is that the difference is in the nature of the Z2 gauge field. Namely, whether it's a background or whether it's dynamical. So let me review the Z2 gauge field on some manifold. For example, we can take our space to be a torus. It has two cycles, call them A and B. And a Z2 gauge field is an assignment of a Z2 Wilson line assigned either plus or minus 1. To each cycle. And now I would say that my symmetry is global if the gauge field is a classical source. So whenever I have a global symmetry of a quantum system, I can imagine turning on a gauge field that couples to that current, couples to that, that symmetry, the current for that symmetry. And so you can view the system in the background of a fixed classical source for the global symmetry. Now this is not something dynamical. The Wilson line is just a number that we choose once and for all and compute correlation functions in the presence of this fixed choice. The symmetry is gauged if we sum over Z2 gauge fields in the path interval. And in this case, the Wilson line is a dynamical quantum degree of freedom. It fluctuates in different states, it takes different values, and it's a genuine quantum operator. In fact, when the symmetry is gauged, then the Wilson line is in fact a topological line operator. And there's sort of a modern perspective on symmetries, that symmetries are the same things as topological operators. And so this generates a symmetry. It generates what's called a D-2 form Z2 symmetry. This is sometimes called the dual or quantum symmetry of the orbifold. That's a lot of words. Let me give it a physical meaning. The physical meaning is that the symmetry counts domain wall number mod 2. at least in the Z2 symmetry breaking phase. So what do I mean by that? Well, if I have my torus, and I have a state where the Wilson line around this cycle is -1, and I look for a symmetry breaking field configuration, say a VEV of a pseudoscalar field, then because as I go around my torus I have to pick up a sign flip of -1, I can't sit in one vacuum throughout the entire space, and there has to be a domain wall somewhere. And this Wilson line just counts the number of domain walls mod 2, and so we have a conserved domain wall number mod 2. Now this is why it's a D-2 form symmetry. P form symmetry is a symmetry under which the charged objects are D-2 branes, so they have D-2 spatial directions or D-1 space-time directions. In other words, they're domain walls. Are there any questions about this?
Just to be clear, the statement is if I have 2 domain walls from the perspective of the conserved charge, it's 0. It's like 0, right?
That's right. So if my Wilson line was +1, I would have 2 domain walls, and then they can just annihilate. I can sit in one vacuum everywhere. Any other questions? Okay. So this symmetry, this domain wall number symmetry, protects domain walls. As long as the symmetry is preserved, domain wall number is conserved mod 2, and they can't decay. So how can we break it? Well, it's broken by vortices, or by cosmic strings. So I told you before that it's a misconception to think that a gauge C2 symmetry always has cosmic strings. The kernel of truth in that misconception is that you always have probe cosmic strings. What does that mean? Well, it means that I can define an operator by cutting out a cycle of codimension 2 from space-time, so some world volume of my vortex, of my cosmic string, and imposing a boundary condition for my path integral over Z2 gauge field, which is modified along this vortex. Namely that as you go around this fixed cycle, my Z2 gauge fields need to have prescribed quantity equals to -1. And so this operator, this you could call a twist operator or a Gupak-Witten operator, it describes the response of the system to a probe cosmic string, and you can also view it as creating or destroying a domain wall. So as I go around this, my Wilson line has to have value -1, which means that I need to encounter an odd number of domain walls, say 1, as I go around. And so if you inserted this in a spatial slice, you could view it just like a local operator creates a particle, this extended operator creates a domain wall. So this is the case where I just have probes. Let me see if I can fit it here. So if I have dynamical cosmic strings, then the dual symmetry, the domain wall symmetry, is broken. And domain walls can decay via the mechanism I described before. Good. So are there any questions about this point? Yes.
Sorry again for asking basically.
No, please.
If you don't allow decay, you seem to do allow annihilation. Obviously, you cannot have domain walls destroy themselves by meeting each other a bunch of times until they're all.
So they can destroy each other if the number is even.
Yes.
Yeah.
Which 50%, right?
Well, so if you're imagining the cosmological scenario,
Yeah.
again, in fact, you know, well, what can I say? In the big cosmological scenario, you produce some number of domain walls, and I agree that topologically they can pairwise destroy, but I'm really asking about the process by which one by itself decays. And that process is precisely asking the question of whether domain wall number is conserved or not conserved mod 2, whether the symmetry is preserved or broken. Good. Is there a clock in here? Oh, I have one here though. Good. Yeah. Many bugs. Okay, so let's talk about parity symmetry. So I apologize if some of that is review. I want to establish some conventions. So parity is not an internal Z2 symmetry. Parity is a space-time symmetry, as I've been emphasizing before. There's a perspective on parity that I think is useful for what I want to talk about, which is to view parity as a composite C2 gauge field, which is built from spacetime, from the spacetime manifold. So what do I mean by that? Well, a composite degree of freedom is something which is not independently summed by itself, but which is built out of some other physical degrees of freedom. So in particular, let's take my space to be a Klein bottle. So again, I can move these like this, but now I move these with an orientation reversal. And you can ask, what is the parity Wilson line around the cycle A? So I'm using a subscript P to denote the parity gauge field. Well, the parity gauge field takes the value plus or minus 1, depending on whether going around some cycle in some manifold comes back with or without a parity flip. More mathematically, the parity Wilson line on the curve C can be written as the integral of the first Whitney class of an ambient spacetime. That is to say that to measure the parity Wilson line, you go along a curve and you ask, did I come back with a parity flip or not? And I want to emphasize that this is not something I can choose independently from spacetime. Once I fix my spacetime manifold, then I fix my parity gauge field. This is what it means to be a composite degree of freedom. So what does it mean for parity to be global? Well, again, global symmetry is one in which I can turn on a background. So this means that I put my theory on a non-orientable manifold. And just look at correlation functions and partition functions in that background. Parity is gauged if I sum over orientable and non-orientable manifolds in a gravitational package. So this is why I really wanted to emphasize the idea that parity is a composite degree of freedom. And if I want to gauge a gauge field which is composite, I can't sum over it as an independent degree of freedom in the path integral. I have to sum over the field which it's made out of. And the parity gauge field is built from the space-time manifold. So if I want to sum over different choices of parity Wilson lines, I have to sum like over the torus and over the Klein model, over different manifolds. Another way to see that it only makes sense to gauge parity in quantum gravity is that the total Lorentz group is a semi-direct product of the local Lorentz group and parity. But parity doesn't commute with local Lorentz transformations. So if I gauge parity, I have to also gauge local Lorentz transformations, which means I pass through a gravitational context. For example, in the context of string theory, world sheet parity, which is usually called omega, is global in the type 2B string world sheet and gauged on the type 1 string world sheet. So I'm talking about the 2D theory of quantum gravity on the string world sheet. This is not a UV complete theory of quantum gravity, but it makes sense to ask the question, and in the type 2B world sheet, we only sum over orientable world sheets. Type 1 string, we sum over both. Okay. So far, it's a little exotic because we're in a gravitational context, but otherwise we have a lot of the similar sort of players. As before, we can ask, how can we count domain walls? So we still have the parity Wilson line, which now that we've gauged parity is a quantum operator in the quantum gravity theory. In fact, it's a topological operator, and it generates a T-2 form, Z2, I'm going to call it parity domain wall symmetry. So if I go back to my Klein model and I look for a pseudo-scalar field configuration, it'll have to have an odd number of parity domain walls around this cycle. And we can ask, can it be broken? The breaking of the symmetry, again, corresponds to the destabilization of the parity domain wall. So we can ask, what would it mean to break this symmetry? So are there any questions about that? So again, we're asking, can it be broken? So as before, we want to look at the object which would break the symmetry. So we want a probe cosmic string for parity. So what would that mean? Well, again, we want to find an operator defined on a codimension 2 manifold. Before we cut out the codimension 2 manifold and define a modified path integral over our Z2 gauge fields, now I want to cut out the codimension 2 manifold and define a modified sum over space-time manifolds. And I want it to be a sum such that when going around sigma, I have some one manifold C with the property that the parity Wilson line on C is -1. And I want my boundary condition to be, at least locally, something of the form sigma cross C. So this is what it means to have a codimension 2 defect in the gravitational theory. I fix this boundary and sum over manifolds outside of the vortex core.
Sorry, I didn't
Yes.
understand that last thing about sigma cross C. What is that?
So the most general, so this is this is D-2, this is a 1 manifold, so this is a D-1 manifold. So it's a boundary for a gravitational path integral over D manifolds. Now, what I'm just saying is that I'm not asking for the most general boundary condition for the gravitational path integral. I want a boundary condition that looks like codimension 2.
Okay.
Right, I want a thing that is extended in some fixed D-2 directions, and I'm just fixing the sort of, I'm saying I'm looking for an object of the right dimension. I'm not looking for like higher codimension objects.
So in the end, the bounded object would be of D dimension, no? Like, because you said it was originally D-2, you had 1 dimension from this extension, and then the thing inside would be the original 3 plus 1 dimension, right?
The whole, yeah, so for example, in 4D, right, this could be, D equals 4, then this is a 2 manifold, and the boundary around it is a 3 manifold, and then I sum over 4 manifolds with this prescribed boundary condition.
Thank you.
And I'm belaboring this point because this is what I mean to have an object of codimension 2. And it's important that I have an object of codimension 2 because, again, I want it to create a single parity domain wall coming off of it, right? This is what it would mean to be able to destabilize via a local process a single parity domain wall. But this is impossible. And it's impossible for a kind of obvious reason, which is that what are the possible 1 manifolds I can choose? The only 1 manifold, or the only connected 1 manifold, is the circle. And the circle is orientable. The circle is just, you can't say I want it to be the circle, but with a parity flip. Once I've said that my boundary condition is of this form, there's no choice of 1 manifold I could put here, which would undergo a parity flip as you go around like this. The sort of thing you could try to do is you could try to flip one of the directions along sigma, but if you did that, you would get an object of higher codimension. You wouldn't get a cosmic string. You would get some object that's more localized in space-time. Maybe another way to say this, equivalently, there is no twisted sector. So the operator I'm looking for is a twisted sector operator for an oriental fold. This is, again, a familiar fact in string theory. Oriental folds don't have localized degrees of freedom because there's no twisted center. Okay. So are there any questions about this? This is sort of it's kind of a simple observation, but this is the main point of the talk. And it shows that parity vortices don't exist. This implies that this parity domain wall number symmetry cannot be broken by any effect. Okay, so that's the phenomenological conclusion. I'd like to switch now and talk about the sort of formal consequences of this observation. But let me again see if there are any questions. Yeah.
Sorry, man.
No, please.
For a non-string theorist, is there any way to say why the only one manifold would be S1?
Oh, this is just a mathematical fact, right? Any one manifold locally looks like a line. If I want to join it back up, I have to. Okay. There's no way to. What you want to do is you want to say that as I go around.
Yeah, I wouldn't want to sound like a Mobius strip, but I guess in 1D you cannot really.
That's exactly the point. Okay, exactly the point. That even though I can have a Mobius strip, right? So the Mobius strip is certainly a cycle, and in fact this is something that I want to discuss. The Mobius strip is a cycle with parity Wilson line along this curve C equal -1. But it's not that the direction along the curve intrinsically flips, which is what I would need for this sort of boundary condition. It's that the direction in the other direction is what flips. In other words, there's sort of a sci-fi thing you can imagine. You go off in a spaceship and you come back, and if you're sort of face the direction you're walking, when you come back with a parity flip, it's your left and right hands that get flipped, not your front and your back. And this is the reason why there's no object of codimension 2. If you tried to do something like this, again, you would end up with an object which is localized in more dimensions than below.
There's no concept of hundredness in
Sorry?
No concept of hundredness in
Yes. Yes. There's no way to. It's sort of an obvious.
Also mathematically forward. Like it sounds reasonable now. That
Yeah, it's just the fact that there's no such thing as a non-orientable one manifold. This is sort of a basic fact, but it's the driving fact behind all of this.
But this symmetry, that's the D-2 form symmetry.
That's right. Yeah. Okay. So this symmetry, good. So let's talk about it. So what is this parity domain wall D-2 form symmetry? Well, what have I told you about it? Well, I've told you that it is an exact symmetry that can never be broken by any effect, and it's compatible with quantum gravity. So you want to say it's a gauge symmetry. And this is what I'm going to say, but it's a little bit weird to think that this is a gauge symmetry. And the reason it's weird is that it's generated by a non-trivial topological operator. In other words, the charge is not zero. It's generated by the parity Wilson line, which is in general not a trivial topological operator. So we have this symmetry.
So what do you mean by trivial topological operator?
So, right, usually when we have a global symmetry, we say it's generated by a topological operator. If that symmetry is gauged, then the topological operator is just the identity. Right? If I insert a gauge flip across, flip spins on the right-hand side, but that spin flip is gauged, then that's the same as not doing anything.
But that should be true, right? Because you project them onto gauge invariant states by summing the bottom to all those two things.
Exactly. In general, that's what you expect. But my point is that that's not true here. This parity Wilson line, which generates the symmetry, is not the identity operator. In particular, in states like this, it takes the value -1. So what it really looks like is a global symmetry. It looks like a global symmetry in quantum gravity, and we don't think that is possible. So I'm going to try to explain how to resolve this tension. This is sort of the.
Is that the case? Because you say you have to sum up the positive rho and values plus usual state.
That's saying that.
Just that is a gauge invariant state. Unless you just adds up, then of course it's not.
That's gauging parity. That's gauging the original Z2 zero form parity. This is the dual symmetry of parity. Right, I've gauged the original Z2 parity by summing over both orientable and non-orientable manifolds. And usually when you gauge a Z2 symmetry, you get a dual symmetry. I'm saying the dual symmetry of parity, I'm going to try to argue you should think of it as a gauge symmetry. But it's a little bit hard to think it's a gauge symmetry because it's not Great questions. And this is what I'm going to try to describe is actually a new effect. I don't know any other symmetry charge that behaves like this one. It's kind of weird. And so that's sort of the formal thing that I want to belabor and spend some time to explain. Good. So to argue that the symmetry is gauged, I'd like to go back and think about the basic reason why global symmetries are forbidden in quantum gravity in the first place. And the basic argument is black hole physics. There's sort of more sophisticated versions of this argument, but essentially all of the physics is contained in what I'm going to say. If I have a global symmetry, I have a point charge Q, global, and I throw my charge into a black hole, then as the black hole evaporates, the charge is deep inside the black hole somewhere. We can't detect that the charge is there, and as the black hole decays away, we should expect the charge to just disappear if we don't allow for remnants or anything. On the other hand, if we have a gauge symmetry, then our gauge charge particle Q is attached to field lines for the gauge symmetry. And when we throw it into a black hole, the field lines remain and they pierce the horizon. We end up with a charged black hole. And we can tell that the charge is in there by doing local measurements on the horizon outside the black hole. And so the process of throwing a gauge charge into a black hole and allowing it to evaporate is completely compatible with the conservation of a gauge charge. The difference is Gauss's law, or remote detectability. A gauge charge is something that satisfies a Gauss law. You can measure it from far away. In other words, it's compatible with the holographic principle, the idea that any property of the black hole can be locally measured on the horizon. So let's ask, what about parity domain wall number? Is it remotely measurable? Is it something that if we threw it into a black hole or a black brane of the right dimension, would it come back out? So to set up the problem, suppose I have a black domain wall. So parity domain walls are domain walls, and so if I want to throw them into a black object, it should be a black domain wall. Let me say that black domain walls are a little bit funny. They have strong back reaction. I'm not going to think about any of that. This is just kinematics here. You can think of this as just a region of flat space if you don't want to think about those issues. And suppose that I have a number n parity domain walls inside my black domain wall, and I want to ask, is there some measurement I can make outside of the horizon that tells me what n is mod 2? And I'm going to tell you that you can. So what do? Tell you prescription. So the first thing we do is fix a convention or a gauge choice that the VEV of whatever effective pseudoscalar field is breaking parity is, by convention, I'll choose it to have a positive sign. This is a gauge choice, but I'm free to make it. And once I've done that, then I can measure the orientation of space-time. So I can look at the horizon manifold, and I can ask what handedness is it oriented in. And there's two things I can find. So suppose I measure a point on the left and right horizon. My convention is that I'm going to orient them by looking out from the object. I can either find that they have opposite orientations or the same orientation. If they have opposite orientations, then because of the conventions I chose, I can have just smooth flat space in the middle. I can just connect them with oriented space with nothing in the middle. And this will tell us that n is even. Of course, I could also have an even number of parity domain walls. If the points have the same orientation, then I need one or an odd number of domain walls so that the orientations can line up compatibly. This will tell us that n is odd. And so yes, so parity domain wall number mod 2 can be measured at the horizon of a black domain wall. And so the conservation of parity domain wall number is compatible with black hole physics. Are there any questions about this argument?
I think it sounds reasonable, but operationally,
Yes.
you can't go passing through the black object, or does it worry you or not?
It doesn't worry me, but it's a good question. So, right, it's very important that you measure both horizons, not just one.
And then compare.
And then compare. I would say that this is always the case. For example, suppose I have a black hole, and I say, well, I'll measure the electric flux except for this region. I'll measure the electric flux here, but not here. Well, then I can't tell the charge, right? Because I could have a bundle of electric flux lines coming out here.
But you can go around.
Sorry?
Or you can go around.
That's
So in
true.
this case, you cannot pass it.
That's true.
That's what I mean.
That is true. In this case, you can't, yes. Absolutely.
Oh, very sure. Of course,
I'll-
mathematically it's okay. Hopefully, you can answer.
Yes,
it's
I-
reasonable, but I'm asking whether that bothers you or not.
Yeah, you're absolutely right that operationally, someone who lives over here, well, here's the case where operationally you could. Suppose that these sides are connected
But it's
far away.
no.
Sorry?
But it's no. It's a coordination one.
No, I'm saying suppose my spatial, this direction, right here I drew it like R, and this is like 0, and it's like the negative reals, it's like the positive reals.
Oh, yeah.
Imagine they connected.
Compact.
It's putting a compact space or something. Or in other words, say that my observers can go far away into a non-gravitational region and then just communicate with.
Yeah.
Yeah.
I think it's incorrect.
Yeah.
Well, okay, so ordinarily, if I have an internal Z2
Yes.
symmetry and I gauge it, I get a B-2 form of global symmetry.
Yes.
Where does this argument break down for that case?
So this argument breaks down because I do the same thing. I fix convention for the sign of my parity, my Z2 internal symmetry breaking condensate, and then there's nothing left to measure. The difference is that in the case of parity, you always have, in addition to whatever local quantum fields, you also have the space-time manifold. And that's what I'm measuring here, right? I'm measuring the orientation of space-time. It's sort of like, even if I have only one field acquiring a VEV, the space-time manifold you could also view as kind of acquiring a VEV under the thing. That's what you're measuring.
So this is going to be true more generally for space-time symmetries that are...
Not in complete universality, but yes, the point in general is that the dual symmetries of space-time symmetries can sometimes just be, they're different. The symmetry structure is different in the automatic negation. I'll say to you that they're described by cobordism as opposed to cohomology.
Okay.
Yeah.
So in usual right, black hole discussions, if I have an electric charge, right, I can have a charged black hole.
Yes.
Can a black hole absorb a domain while become a domain charged under parity domain, like black hole? Like, is there a meaningful sense in which you can still get a metric solution which is charged under parity?
Yeah, so I didn't want to look for a metric solution because the objects I'm talking about are domain walls, so I need to look at a black domain wall, and those are difficult. In general, if I want to talk about a conserved charge of a p-dimensional extended object, I should throw it into a black key ring. So if I have a string charge, I should throw it into a black string. So usually if you think about point particles, you throw it into black point particles over black holes.
So this would be like a black hole into basically.
This would be like a 2D black hole. Yes.
And then, okay, yeah, I mean, we can have that, right? I'm used to more 5D objects, right? We can have like a black hole horizon in fifth dimension. But
Yeah.
In general, that would mean that, yeah, such objects can absorb like this.
Yeah, exactly. So the metric here, I could be a 2D black hole times R whatever else I need to. Yeah. The thing that's weird about black domain walls, right, is just, it's just a fact about low dimensions and the back reaction gets drawn far away from them. It's not essential to any of the sort of kinematic questions I'm asking. Again, I'm assuming that my theory is I'm working in some theory which is a UV complete theory, not some unusual low dimensional example. Okay, great. So are there any more questions about this argument? Because so let me now finish up by saying how you can reconcile this argument that this is the C2. So I just argued that the parity domain wall number is gauged with the fact that the parity Wilson line is a non-trivial topological operator. So what about the parity Wilson line? So as I said before, the parity Wilson line is certainly a non-trivial operator. Right, you can have, again, as I drew, a Mobius strip with a curve C, which has parity Wilson line -1. And so I sort of said the answer before. There's a difference between the directions along the curve and the directions transverse to the curve. Mathematically, what I can do is I can recall that the Parity-Wilson line along my curve is defined in terms of the first Stiefel-Whitney class of the ambient space-time. Right? When I go around a curve, I ask how much does my ambient space-time flip. But the first Stiefel-Whitney class is additive, and along the curve C, the first Stiefel-Whitney class of the ambient space-time is the sum of the first Stiefel-Whitney class of the tangent vectors along my curve, plus the first Stiefel-Whitney class of the vectors normal to my curve in the orthogonal directions. And this first part always vanishes. This is saying that going along the curve you never encounter a parity flip. This part can be non-zero, and so this part can be non-zero. In other words, the Parity-Wilson line measures, is a quantum operator, which measures the topology of the normal bundle of the curve. So this is only a sort of operator that you can have in a quantum theory of gravity where the normal bundle is fluctuating. And so the proposal that we wanted to make is that if you have a symmetry such that the charge vanishes. So normally if I had a gauge symmetry, I would say that the charge should vanish on all closed manifolds in space-time. This is Gauss's law. This is saying the net charge on a closed slice under a gauge symmetry is 0. But let me say that it only vanishes on all normally framed submanifolds. So this is, I only impose Gauss's law on submanifolds with the normal bundle being trivial. Then I want to say that this is a gauge symmetry. So this is a weaker notion of gauge symmetry than normal, but this is enough for the properties we've seen before to hold. This is enough for it to not be able to be broken by any object of the right codimension, and such a charge could also be measured at the horizon of a black object. Because in both cases of looking for a vortex or measuring it inside a black brane, the directions along the object we're looking at provide this trivialization of the normal directions. And so such a charge that satisfies this weaker version of Gauss' law behaves as a gauge charge for these sorts of purposes that come up in quantum gravity. Maybe 2 words of further motivation. So the first is that to support it. Yeah.
Sorry, I'm having a little bit of trouble wrapping my head around that. How do I understand that compared to the usual Gauss law constraint?
So the usual Gauss's law would say that the topological operator of my symmetry on any mk of the right dimension is 0. Here I'm only imposing it when this is a normally framed submanifold. In particular, I'm saying I'm not imposing it like here. Right here, the Parity-Wilson line takes a non-identity value.
Okay.
Sorry, equals 1. Right? So I'm only imposing I'm only demanding the net charge vanish on manifolds where the normal directions don't flip around, which is weaker than usual.
Okay, so I can see how this is clearly not going to apply to internal symmetries. Like
this will never show up as internal
can't show up
symmetries.
there. Okay.
Yes, this is a purely gravitational effect because essentially what's happening, maybe I can make this comment. One way to understand this is that charge should be measured in Hilbert space. And a Hilbert space requires the choice of an arrow of time. If I want to quantize a theory on some spatial slice, I need to choose a direction to call forward in time and quantize in that direction. And so to define a state, I need to choose this normal framing, this trivialization of the directions transverse to the slice where I'm quantizing. And when I demand that charge should vanish, I should only really demand that the charge of a state should vanish, the charge of a quantum state. For higher form charge, I should look at higher categorical analogs of Hilbert spaces, but the same logic applies. Another sort of piece of motivation for this is that such a symmetry is not broken by replica wormholes. The reason is that there's been a number of recent nice papers that have explained how charge flowing through a replica wormhole can violate global symmetries, the idea is you take two copies of your original system, and a replica wormhole lets charge flow from one copy to the other, so in each copy the charge looks like it's not conserved. So suppose I have two copies, I and j, for I is not equal to j, and I ask, can such a charge flow through?
Sorry, what is that, Jay?
I and j are my replicas. Sorry, who asked?
Sorry, I just understand I is not equal to j. So.
I mean that I'm doing I'm computing something via a replica trick, and I'm taking two distinct copies of my system, as opposed to the same copy, like off the diagonal in replica space. And in such a case, if you take, this is a bad drawing, let me try to make it a little better. If you have a replica wormhole, and you ask, is there charge flowing through it? Then what I do is I take a slice, I look at the topological operator measured on the slice, and if it's non-zero, then I can have my supposed global charge flow from one replica to another. But precisely the direction from my first copy to my second copy is a normal framing of the slice through the replica wormhole. So a charge that only satisfies this weaker Gauss law will not be broken by replica wormholes. Okay.
So it's a statement that otherwise you could have gotten a quote-unquote effective decay to the replica copies, whatever?
Yeah. The idea is that there's been some recent, a number of recent works, sorry, who asked? Yeah, the idea is that there's been a number of recent works that argue for universal violation of global symmetries in quantum gravity using the replica trick, and using this as a way to argue for the violation of global charge. And my point is that if you're unsure as to whether this is a global or a gauge charge, the fact that it isn't violated by the replica trick means that it behaves more like a gauge charge. Right, gauge charges are also not violated because, again, they can't flow through the wormhole. Yes?
Sorry, this is going back to Tom's question. So you're demanding a weaker proposal where you're demanding Gauss's law only for normally framed submanifolds?
Yeah.
So this is probably my question, but how do I think of Gauss's law for a manifold that is not framed?
That is not normally framed?
Yeah, like is there even a notion inside and how do you think of the notion inside and outside?
So the naive thing you want to say is that one version of Gauss' law, right, says that the net charge in a closed manifold vanishes. And the reason is that you have positive negative charge, they radiate gauge field lines, they'll have to go end somewhere, and so the charge has to vanish. In terms of topological operators, it's a statement that the symmetry operator inserted on any closed slice is the identity operator. It acts, but gauge transformation should be trivial actions on the physical degrees of freedom.
Yeah.
But my point is that here it's not.
Right, but also, I guess what I mean is I don't know how to think of a surface that encloses something because I don't have is it easy to have a notion inside or outside?
Oh, sorry, there's two things being mixed up here. So Gauss's law in the context of black holes is the version where you want to say, I want to measure the net charge in a spatial slice, so I measure the electric flux on the boundary. The version I'm saying is measure the net charge on a closed spatial slice.
Oh, I see.
And usually we say that vanishes because the flux through the boundary is zero because the boundary is empty.
Okay.
Yeah, I think you're off by one in the dimensions in what you were asking.
Okay. Anyway.
Yeah, I want to measure the net charge in a whole slice, not on the thing that the slice bounds.
Right. Okay, but usually you can just use Stokes' theorem to get it to the boundary. Right?
Yes. My point is that Stokes' theorem on a closed manifold tells you that it's just zero.
Oh, okay.
Right, Stokes' theorem tells you that an exact form on a integrate over a closed curve is zero.
Okay.
So let me say some conclusions, and maybe some comments as to what the sort of general picture of this sort of charge is. And then I'll wrap up. So the basic physical intuition is that while you can go around the curve in space-time and pick up a parity flip, you did not go around a parity cosmic string. And this mismatch is sort of the source of the confusion in the literature about these parity cosmic strings in Nelson bar models. It's sort of natural to think that because you can go off in a spaceship and come back with parity flipped, then you must have gone around a cosmic string for parity. Therefore, parity domain walls can decay via nucleation of parity cosmic strings. And what I'm telling you is that that's false. That's not true. Parity domain walls are exactly stable in Nelson bar models. So that's the pheno implication, is that parity domain walls are stable. And in particular, if you want a realistic Nelson bar model, you have to inflate them away. You don't have any choice. And that sort of puts very severe constraints on your parameter space. And then there's this formalization of precisely this mismatch in terms of this weaker Gauss's law that I only impose on manifolds with normal framing. And the comment I just want to end on is that there's many more examples of such charges. Mathematically, you get such an example whenever you have a characteristic class, in this case W1, that vanishes on all manifolds of the same dimension. And there's tons and tons of such examples. For Stiefel-Whitney classes, they're called Wu relations. In general, they're described by what's called the Adams vector sequence. And I'd like to know what their physical meaning is. I think there's a lot more things to sort of think about and ask, can we derive some, sort of real physics like this from these other sorts of charges? So thanks, and I'm happy to take questions.